So is my screen visible to all of you?
Yes, ma'am.
Okay. So good evening all of you. We are going to discuss about the course Introductory Organic Chemistry Part 2, which is an NPTEL platform course. And the course instructors are Professor Harinath Chakrapani and Professor Niraj Dashaputre from ISER Pune. And I am Simran, your PMRF teaching assistant. So we have discussed till far 7 lectures. So 7 topics we have covered. And the topic for today is the rearrangement reactions. So, before going to this rearrangement reactions topic, I would like to know whether you guys have gone through my NPTEL platform videos. And if you guys have any doubt regarding any of the lecture, then please tell me now. If anyone has any doubt regarding the previous sessions we have taken, okay, then if not, then I am going moving to the week 8 topic, that is rearrangement reactions. Okay. So, with the problem number 1, they are asking you identify the major rearrangement product of the following reaction. So, this is the tricyclic compound which you have. Now, you have to predict the product which is there after treating it with HCl. That is the acid they have treated it with this particular bicyclic compound, and you have to tell the final product of this rearrangement product. So, can anyone tell me if you have a double bond here, then what would this HCl do? First of all, what will this acid do? See, I have told you that double bond is electron rich species, right? So
Nucleophilic
if
addition.
yeah, so here first of all, this acid will protonate your double bond, that is the electron rich species. So here the protonation can be happen on two carbons, either this carbon or this carbon. So basically, protonation at this carbon will give you a carbocation at another carbon, and protonation at this carbon will give you the carbocation on the another carbon. So if I am telling you that this is one and this is two, then if protonation is happening to carbon number one, then the carbocation is forming at carbon number two. But when the protonation is happening at carbon number two, then the carbocation is carbon number one, which is forming. So, can anyone tell me which will be the favorable pathway of the formation of carbocation? One or two? Which is more stabilized carbocation? So, as you can see here, if the protonation happens at this position, then the carbocation which is forming at this position is highly stabilized. Why? Because it is a tertiary carbocation. But if you see at the carbon number one, that is this, then the carbocation is secondary carbocation. So that is why the protonation will prefers to happen at carbon number one, so that the carbocation can form at carbon number two. That is this carbocation. So this carbocation is highly stabilized due to the tertiary carbocation. So here after formation of the carbocation, now what will happen? If a carbocation is formed at this carbon, then in the presence of acid, what will happen? This bond, basically the four membered ring which is present here, this is a highly strained ring, right? So it has a tendency to open up. So if it has a tendency to open up, what it would prefer is it would trap this carbocation. So this CC bond will break and a new CC bond is now going to form like this, right? So now this CC bond is going to break and this is going to be formed. So now this carbocation is forming at this position rather than this. So there is a migration of this bond from carbon number 1 to carbon number 2. Why? Because to release the strain which is there because of the presence of four membered ring which is highly strained. So the driving force here is to neutralize the carbocation charge but to free the strain of cyclobutane ring to form the cyclopentane ring. So here four membered ring is converting it to the five membered ring, that is why strain is getting released. That is why here CC bond is getting cleaved. So here this CC bond is getting cleaved and this CC bond, which is a new bond, is getting formed. So now this positive charges remain there at this carbon because now after cleaving of this bond, there is a positive charge at this side. So in the question itself, they have given you a HCl. Cl we know that it is a good nucleophile, right? So it would act as a nucleophile and it will trap your positive charge, that is the carbocation, to give you the Cl at this position. So basically, you have started it with this bicyclic compound, and now in the presence of acid, first of all, the protonation is happening at this position. I've told you why, and then there is a bond migration which is taking place to release the strain of this butane ring and to form the pentane ring. So here, this cyclopentane ring is getting formed, and after the formation of this carbocation, it is getting trapped by the nucleophile which is coming from the acid. So you will get the product, that is this. So is it clear the mechanism of this reaction? Am I audible? Am I audible to all of you?
Yes, ma'am.
Okay, then please answer me, na, so that I
Yeah,
can.
ma'am. Please proceed, ma'am.
Okay. Okay, so I hope it is clear to everyone the mechanism of this rearrangement. So, so now tell me which is the correct option among these four.
Option 1.
Option number one. So option number one will be the correct one. Okay. So it is nothing but the Wagner-Meerwin rearrangement. So here the carbocation stabilization and the ring strain will play the role of forming this compound. Okay. So I hope it is clear to everyone. Now moving to problem number two. So in problem number two, they are asking what is the major product formed in the following rearrangement reaction. So now you have to identify the product of these three reactions. So first of all, what they are doing is they have taken this ring and they are doing the Wittig reaction, right? So this halide will attack onto this ketone and to form this alkene. So in the previous lecture, I have given you the mechanism of the Wittig reaction, and also in this lecture also we will be seeing the reaction of mechanism of Wittig reaction. Okay, so previously I have discussed it that if you have treated it with this halide and ketone or aldehyde, you will get the alkene. You will get the corresponding alkene. So here they have used the Wittig reaction to get the alkene, and then the alkene is subjected to osmium tetroxide condition. And we also know that in osmium tetroxide condition, dihydroxylation is going to happen. So in both the carbon, dihydroxylation will takes place. So this alkene carbon now get dihydroxylated. Okay, to get you this particular species. So this much they have already provided you. Now you have to answer the major product of this rearrangement. So you have to identify this product. So they have treated this diol with tosyl chloride pyridine. So when you are treating this with tosyl chloride and pyridine, what will happen? The OH is getting protected by tosyl group. So tosyl group is nothing but it is the para-toluene sulfonic chloride. So here, what will happen if you treat it with tosyl chloride? So it is a protecting group. So it will protect your alcohol So first of all, the primary alcohol is getting protected by this tosyl chloride in pyridine, and then the secondary one. So here they have not added, like, they have controlled it, and you have to protect only the primary one. So the protection of primary alcohol is easier than the secondary alcohol, and the secondary protection is easier than the tertiary alcohol. So there is a order of protection which is there. So primary alcohol is getting protected by the tosyl chloride by giving you OTS at this position, and after that now you have to carry out the rearrangement reaction. So I have told you previously, this is again the example for the Wagner-Merwin rearrangement. So here, as OTS is a good leaving group, it is a very good leaving group. So it will leaves out, giving you a carbocation, which is a primary carbocation. It is not stabilized. So now it will prefer to go to a secondary or tertiary carbocation rather than to forming the primary cation. So here, after the release of this OTS, that is a leaving group, what will happen? At this position, you will get the carbocation. Now, at this position, there could be two possibilities. So here, migration of this CC bond at this carbocation can take place to get the carbocation at this carbon. Because now here, CC bond, this CC bond is getting cleaved, right? So this carbon is making another bond with this carbon, but this is getting cleaved. So after cleavage, there is a positive charge that is forming at this position, and this is getting formed. That means the positive charge at this primary cation is getting neutralized. So here, what is the driving force for doing so? Because of the presence of this OH. What will happen after the formation of carbocation here? Your lone pair of oxygen, now they will stabilize the carbocation which is forming at the adjacent carbon by donating the lone pair of electron. What will happen? You will get this species after the disconnection and the remaking of the CC bond. You will get a 8-member ring, 8 member or 7 member ring. So here you will get a 1, 2, 3, 4, 5, 6, and 7. So it is a 7-member ring formation, and this carbon having the OH group will get a positive charge. So here the carbocation is stabilized by the lone pair of oxygen. So lone pair will come down, and it will neutralize this carbocation, and this hydrogen will leave out to give you a ketone. So this is how the rearrangement is going to happen. So first of all, you have taken a diol, you have treated it with tosyl-chloride pyridine. What will happen? The protection of diol will take place, but as you can see here, one is the primary alcohol and another is the secondary tertiary alcohol. So here the protection of primary alcohol is easier than the tertiary alcohol. That is why first of all the primary alcohol is getting tosylate, and after the formation of OTS group, what will happen? It will leaves out because it's a very good leaving group. So here the formation of positive charge will take place. So this will neutralize by the migration of this CC bond. So basically this CC bond cleavage will take place to form this bond to get this positive charge neutralized, and the driving force was that after the formation of this positive charge, this is neutralized by the lone pair of hydroxyl group to give you the ketone. So is the mechanism under? Did you get the mechanism, guys? Is it understood?
Yes, ma'am.
Okay. So if it is understood, then tell me which is the correct option among these four.
Option C.
Option C. Yes. Option C will be the correct one. Okay. So this is how you have to proceed for these kind of rearrangement problems. You have to think what sterics, what thing will stabilize a carbocation, how you are going to migrate the bonds. So you have to see that things in mind. Okay. So coming to problem number 3, if you have understood this. So in problem number 3, again they are asking you the major product of the following reaction. So you have to identify the product. So what they have done, they have done the reaction of ketone with acid in the presence of acid. So basically, you have this four-membered spirocyclic ring with this ketone functionality in the presence of acid. So now, tell me what this acid will do. Already we have discussed this in the previous lectures. So this acid, what it will do? It will protonate your carbonyl oxygen, right? So it will protonate your carbonyl oxygen. So it will make this carbon more electrophilic in nature, right? So the carbonyl carbon is now having electrophilicity which is increased after the protonation of the ketone. Now tell me which bond will migrate. See, you have to, if you are going there, if this bond is going there to neutralize this positive charge of the electronegative carbon oxygen, then there is a species which is forming is that you have a OH at this position, right? The single bond and carbocation which is forming at this carbon, right? And you have this four-membered ring with you. So now tell me, will how what will migrate here? Like you have to neutralize this positive charge, right? And you cannot do this कि हम ऐसे न्यूट्रलाइज कर सकते हैं. It is not going to like that, because if you are going to do this, what you will end up is the reactant only, right? So you are not going to do this, because in the presence of acid, the lone pair is not going to come back and give you the starting material only. So here, after the protonation, the second step would be something else. So can anyone tell me what would be the second step of this reaction?
Migration of
Migration of the carbon carbon bond. So which bond will
carbon
migrate?
carbon
See,
bond.
I have told you that the
Four
cyclo,
member ring.
yeah, cyclobutane ring is highly strained. So here, this bond will get migrate to this. So here, this bond will migrate to this carbon. So this is how it is happening. So first of all, protonation of your carbonyl, then this migration is taking place. So this CC bond will migrate to this carbon, and again your carbocation is forming at this position. See, this bond is getting cleaved. You have to think about that this is getting cleaved and this is making, right? This is the bond which is formed. So this is cleaved. So if this is cleaved, then the carbocation will be at this junction, right? Because it is neutralizing by forming a bond with this. But this carbon has a positive charge. This is how you get the positive charge here. But now this positive charge is not in the proximity of this OH, right? So you cannot do the lone pair pushing. So what you can do here is, as I have told you that five-member ring formation from four is highly favored, but also five-member ring is the favorable ring and the stable ring, in fact, from the six-member ring. So five-member ring is very stable. So here also, keeping the same concept in mind, what will happen? This CC bond again migrate. So what is the driving force of the migration? First is the formation of the five-member ring, and the second is that you will get a carbocation at this position, this carbon, and you know that this lone pair can neutralize that positive charge very well. So here also this CC bond is going to be cleaved. So now this bond is going to be formed. So this is the bond which is getting formed. It is getting cleaved, right? So if it is getting cleaved, you will end up having a five-member ring fused, with the spiro connection of the five-member ring. So after formation of the positive charge here, you know the next step that it will come here and you will get a ketone. So you will get a spirocyclic moiety 5 plus 5 starting from 4 plus 6. Okay. So is it fine, guys? Everyone understand this particular rearrangement?
Yes, ma'am.
Okay, so if it is understood, then which is the correct option?
Last option D.
Last option. That is option number 4 will be the correct one. Okay. So moving forward to problem number 4. It is also a similar kind of problem. So here they are asking you the major rearrangement product again. So you have to identify the product. So in presence of acid, I've told you that in if ketone aldehyde, any carbonyl compound is there, first of all the protonation will happen. So if the protonation is happening, then what will happen? This is going like this. But now there is one thing that these double bonds are in conjugation with this carbonyl. So here also it will migrate to stabilize that carbocation. So now if it migrates, then there would be a formation of carbocation at this position. Just think about it. 1, 2, 3, and 4. Right? So if 1 and 2 bond is becoming a single bond, right? For the neutralization of the positive charge which is acquiring at the oxygen due to the protonation. Now there is a bond migration which is taking place, basically delocalization, and there is a partial double bond which is forming between 2 and 3. So this 3 and 4 is again going to be a single bond. So at 4 position you will get your carbocation. See, this is how it is done. So basically there is a carbocation which is ending up at this fourth position, right? So now again what will happen? I have told you wherever you are seeing this particular four membered ring, just identify that it is going to release the strain. It is very much willing to release a strain because it is highly strained molecule. So whenever it gets a chance to release the strain, it will release the strain. So here also it is getting a chance to release the strain. So positive charge is formed at the vicinity of this particular cyclobutane. So here this CC bond will going to be migrate at this position, and this bond is getting formed, right? And this bond is getting cleaved. So if this bond is getting cleaved, you will get a positive charge at this position, right? So after having this positive charge, your four membered ring is getting into the five membered ring. So this is the five membered ring now, which is fused with this. Now it is not spiro, but a fused ring with the five membered ring. So here 5 plus 6 fused ring is going to be formed. So here the positive charge is again neutralized by the aromatization. So this is something different from OH, but here the aromatization is stabilizing your carbocation. So here additional thing is, first of all the driving force is the ring strain, and the second is the aromatization. So second point is the aromatization. So basically, whenever your ring is getting a chance to get aromatized, it will get aromatized. Fine. So it is the aromaticity and the ring strain. So now you are getting a five membered ring which is fused with six membered ring starting from the spiric compound. So can anyone tell me the name of this rearrangement? It's a particular name for this rearrangement. Anyone knows the name? Okay. So let me tell you the rearrangement name is dinon phenol rearrangement. So basically it is the dinon phenol rearrangement. So here basically you have the enon moiety and you are converting it into the phenol moiety. That is this phenol. So dinon phenol rearrangement is this particular example. Hmm. So previously we have seen about the Wagner-Meerwin rearrangement. So here there is something else, because here your moiety is converting from the dinon to phenol. That is why the name suggests this particular rearrangement. So is it clear the mechanism for this rearrangement, guys?
Yes, ma'am.
Okay. So if it is clear, then the answer is option number 1. Right? So option number 1 will be the answer for this question. So now coming to problem number 5. So in problem number 5, you have to identify the major product of the given reaction. So again, they have given you the diols, but they have treated it with acid. They have treated it with strong acid, that is the sulfuric acid. So in the presence of acid, what do you think will happen? Anyone?
Extraction of water molecule.
Okay. So here, the protonation of diol will take place, right? Because your oxygen has lone pair of electron, it has H plus to give, right? So here it will attack onto your H plus and it get protonate. So which alcohol is going to be protonated? One or two? So now you have to consider that after the protonation, it is converting into OH2 molecule, that is the water molecule. So it will leaves out because the neutral species removal is very easy. It is stable. So as a good, because now OH is not a good leaving group now. So after protonation, it is becoming a good leaving group. So after protonation, the water molecule is leaving out to give you a carbocation. So if the carbocation is to be formed, then there is two options, either to form at this carbon or either to form at this carbon because you have diol. So just tell me the carbocation stabilization if we see, then at which position the carbocation is more stabilized? Carbon number 1 or carbon number 2?
Carbon number 1.
Carbon number 1. Why? Because here benzyl carbocation is getting formed. And benzyl carbocation has a greater stability than even tertiary carbocation. Okay, so here benzyl group is giving the, this phenyl group is giving the extra stability to this carbocation formed. So here the formation of carbocation at C2 position is highly unfavorable. In fact, it is a tertiary carbocation, but it is present on the ring, so which is not favorable and it is not as much stable that than this benzyl carbocation. So the carbocation formation will take place at C1 readily. So after the formation of carbocation at C1, now what will happen? So if the C1 carbocation formation is taking place, it will leaves out this OH2. So now positive charge is going to be formed at this carbon. So now I have told you that this OH, if you have any OH present in the group and the CC bond can migrate to form a carbocation, it is stabilized by the lone pair of the oxygen. So here also your 5-member ring will, this CC bond will migrate, it will become a 6-member ring, right? So this will migrate. So what will happen? This bond is forming and this bond is breaking. So if this bond is breaking, then this carbon will get a positive charge. And we have discussed that after formation of the positive charge at this carbon, what will happen? Your OH bond will cleave, it will go down to give you a ketone. So you are getting a ketone moiety, a 6-membered ketone when we started with diol having a 5-membered. So please go through this mechanism and tell me anyone has any doubt regarding this mechanism. Okay, if not, then tell me now which is the correct option.
Second option.
Second option will be the correct one. Okay. So this is the What is the name of this reaction? Can anyone tell me? It is also a name rearrangement. So it is the phenol rearrangement, right? So this is the phenol rearrangement. So this is the phenol, that is the alcohol. Phenol means you are getting a ketone. Okay. So based on the starting material and the product, you can suggest that yes, the name will justify the product formation. This is the phenol rearrangement. So I hope it is clear to everyone. So I'm moving forward with problem number 7. So you have to identify the major product expected when 2s 3 dimethyl cyclohexanone is treated with MCPBA. Okay, so they have treated this chiral compound, that is 2s 3 dimethyl cyclohexanone, with MCPBA and fish oil. So metachloroperbenzoic acid they have treated it with. So now tell me which could be the possible answer for this mechanism. So we have discussed about the chemistry of MCPBA, how it works. Can anyone tell me what could be the possible answer for this question? Okay, so brush up your things. To brush up your things, I'm just giving you the mechanism. So this is known as bare vinegar oxidation. See, I have told you whenever you have this MCPBA, na, it can act as delivering oxygen at the adjacent carbon of the carbonyl group, or it can give you the epoxide ring formation. But here there is no double bond, there is no alkene ring which is competing with the bare vinegar oxidation. So there is two possibilities: either the bare vinegar oxidation takes place or the epoxide ring formation will take place. So if you have a double bond in the compound, then it will compete with that particular reaction of formation of epoxide. But here we are only having the carbonyl group and no alkene, no double bond which is present to get epoxidation. So that is why simply you will get a bare vinegar oxidation using the MCPBA rather than any other epoxidation reaction. Okay. So what is the mechanism of bare vinegar oxidation? So here, first of all, what will happen? This ketone will react with, what is this, meta chloroperbenzoic acid. Basically, your perbenzoic acid is given here, and R is the metachloro. So this is the perbenzoic acid. So it will, first of all, it will protonate this carbonyl oxygen. So it will get protonated, and this acetate will leaves out, right? So now this peracetate will then attack again onto your carbonyl carbon, because now it is becoming the electrophilic, highly electrophilic. So now this nucleophile will attack onto your carbonyl carbon to give you this kind of complex. So after the removal of this OH, it will come down, and this carbon basically, this CC bond is now migrating to take this oxygen, and this acetate will leave out. So this is the main key of this reaction. So here, first of all, the protonation takes place of the carbonyl compound. Then the nucleophile which is forming, that is the peracetate ion. It will attack onto the carbonyl carbon to give you this complex. And after that, the base will abstract the proton, and it will give you the ketone moiety here. But one CC bond migration will take place. So here CC bond migrate to take up this oxygen, and it will go out. So after taking up with oxygen, this ring expansion is taking place. So this 6-membered ring is now going to form the 7-membered ring. So with ketone, with having a adjacent oxygen. So now here you will have 1, 2, 3, and 7. Right? So if you number it, it is also, so I should number this carbon as 1. Okay, not this oxygen. this is 1 having linked with 7, and this is 6. So remaining you can see wherever the functionality is. So here at 6 you have methyl, at 6 you have methyl. So here after the formation of this, and the acetate again take up the proton from the base and give you the acid with this particular species in hand. So if I subject this kind of mechanism to this particular species, what will happen? There is a possibility of migration. Either this bond can migrate or either this bond can migrate. What did you mean by migration? See here, I have told you after the attack of this acetate per acetate, this species is going to be formed. So there is two possibility: either this bond can migrate, either this bond can migrate, right? Because this is the carbon having a methyl substitution, it is getting migrated. Why? Because those carbon is getting migrated having the higher electron density. Why higher electron density? Because now this oxygen is electrophilic. It is not nucleophilic, it is electrophilic. It had attacked on this particular carbonyl carbon, and after that it becomes neutral, like electrophilic basically, because this OO cleavage will take place and the acetate is gaining the negative charge. So here this oxygen is not nucleophilic in nature. That is why the carbon which is having more electron density will migrate to take up this oxygen rather than the carbon having lower electron density. So similarly at this position also, if we see that this particular carbon is moving rather than this particular carbon. Why? Because the electron density at this carbon is high due to the presence of methyl group. So it will take up this oxygen and this acetate leaves out, and you will get a oxygen at this position at the right rather than left. If this is highly electron rich, then you will get this bond migrated with oxygen and you will get oxygen at this position rather than this position. So is it fine? Is it understood, guys? Why this position is getting an oxygen rather than the right hand left hand side? Is the mechanism clear to everyone?
Yes, ma'am.
Okay, so if it is clear, then tell me in this case which bond will migrate, one or two?
Two.
Two. So what will be the product among these four? Option number
Second one.
second one. Why second? Because as you have inserted an oxygen between this CC bond because of the electron density at the second position, that is right. But here your stereochemistry is getting changed in C and D. So this bare Willinger oxidation has nothing to do with your stereochemistry. It will remain same, but your C bond is getting an oxygen inserted. Okay, so stereochemistry will remain same. So second, that is why the B part is the correct one. So now coming again to the problem number 8. So here you have to identify the correct intermediate through which the Wittig reaction proceed. So there come the Wittig reaction. So here also they have treated the ketone with the Wittig salt. So you have got this alkene formed, right? So they are asking the correct intermediate. So can anyone tell me based on the mechanism of Wittig reaction, which will be the correct intermediate for this transformation? So let me make it simple for you. First of all, Wittig salt. So what will happen? This carbon ion will definitely attack onto your carbonyl carbon, which is electrophilic in nature. It will go up having a O minus. Now, if your O minus have negative charge, that is nucleophilic, then it again will trap to your phosphorus, right? To make a, how many membered ring it will make? how many member ring it will make? A four member ring, right? So based on this four member ring formation, so I think you have to revisit the Wittig reaction mechanism. So what is happening in the mechanism? So first of all, attack of the allyl carbon on the carbonyl group. So basically this is the allyl. So it will attack onto your carbonyl carbon. It is electrophilic in nature. This O minus which is getting formed after the attack, this O minus will attack onto your phosphorus to give you a oxaphosphetane ring. This is the oxaphosphetane ring. So this betaine ring will then collapse to give you the alkene and phosphine oxide. So this is how you are getting the alkene ring form. So now tell me which will be the correct intermediate among these four. Here I have already showed you the mechanism, right? Okay. So if you are not going to answer it, then I am answering. So here, what will happen? A four-member ring is getting formed, right? Simply, this is the intermediate which is known as the oxaphosphetane ring. So here, in this option number one, they are telling you that this negative charge of I don't know what is happening. So basically, they are connecting this carbon to this phosphorus, which could not be possible, right? So according to the mechanism, also according to the things, also it cannot form the bond with the CP. So now coming to part number three. So here, if you see, you will find that there is a what is the problem with this? Here, your this attack is fine. That is the C carbon. This carbon one by one is attacking onto your carbonyl carbon, right? But the O minus which is forming again is going to react with your phosphorus, not the carbon which is adjacent to the phosphoryl ring, right? This carbon is not at all reacting, not at all taking part into your Wittig reaction. That is why it is not possible, so it cannot be possible. So remaining is this particular option only. How it is correct? First of all, this carbon is getting attacked onto this particular electrophilic carbonyl carbon, right? So this bond is getting formed. After that, this O minus is forming bond with pph3, right? So this is the particular four membered oxaphosphetane ring which is going to be formed as an intermediate in reaction which is known as Wittig reaction, right? So the option number B will be the correct. So is it understood, guys? This much? Okay, so if it is fine, then coming to problem number 9. So in problem number 9, they are asking you osmium tetroxide mediated dihydroxylation of the following compounds led to the formation of the following diols as exclusive products. So basically, reaction A is giving you this diol, reaction B is giving you this diol. So you have to answer the correct option basically. You have to choose the correct option. So they are asking you, as shown above, in reaction A, the approach from top phase is preferred. As shown above in reaction B, the attack from the bottom phase is preferred. The methyl group hinders the approach in B, and a reversal in facial selectivity is seen, or all of the above. So can anyone quickly tell me what is happening in this reaction and what is the correct option? So it is a very straightforward reaction. So what could be the possible answer for this? So let me make it clear for you. So here, osmium tetroxide based dihydroxylation has to happen, right? So I have told you previously, osmium tetroxide is a dihydroxylation reaction. So basically, your hydroxyl have to come from the same side. So in this osmium tetroxide mediated dihydroxylation, if you see the mechanism, you will get to know that both the OH should be coming from the same side. So basically, if one OH is coming from one above the plane, then the second is also coming from above the plane. So basically, this is a syn attack which is taking place. Okay, just go and check the mechanism for this reaction, but you will understand that the attack is the syn attack. Okay, So if it is a syn attack, it has two possibility: either the OH will come, both the OH will come from above side, or both the OH will come from downside. So in this reaction, both are preferring to be above the plane because the protons are present at this bridgehead position. So basically, there is no hindrance which is present in the reaction A because there are protons which are present in the proximity, right? But if you compare this product with the product in which OH is downside, both the OH is coming from the below the side, then what is happening? As this is a bridge molecule, as is the bridge compound, and it is a envelope kind of structure. So these two hydroxyl group is facing the steric hindrance because of the cavity which this particular molecule have. So there is a cavity, na? That is why it is making the below side attack hindered rather than the above side attack. So if I prefer to go from A side or to B side, if I have an option to go either from A, either from B, then I'll prefer A side. Why? Because there is no steric hindrance from the above the plane, but below the plane, due to the cavity, there is a steric hindrance. Okay, so that is why reaction A is performing like this. But when you come across to reaction B, now what is the significant change? Here there is the methyl which is present at the bridgehead position rather than hydrogens. So similarly, now here also OH has two possibility: either to come above side, either to come down side. So it will prefer either A, it will prefer either B, right? But as I have told you that there is a cavity which is present at this position, but the extra destabilization which is present in this molecule, if the attack is going to be taken by the above the plane, what is happening here? Methyl, two methyl groups are present here, which is giving you the steric hindrance to the upcoming nucleophile. So here there is a steric hindrance due to the presence of the bridge head methyl. So that is why the attack from the cavity is preferred rather than the above the plane attack due to the presence of methyl. So as we have seen here in the reaction A, when hydrogens were there, the attack was from above the plane. But when you are placing hydrogens from methyl, then the scenario is now straightforward different. What is happening? Attack will take place from the B side rather than the A side. So that is why you are getting this particular compound formed, not the above the plane hydroxyl groups. So now tell me which is the correct option. I have explained all the things. Just read out the options and now tell me which is the correct one. So first one is saying as shown above in
All the above.
all the above. Because in reaction A, the approach from the top face is preferred. Yes, we have seen. Sorry? Okay. So in reaction B, the approach from the bottom face is preferred. Yes. When you go to C, the methyl group hinders the approach in B and the reverse is in facial selectivity seen. Yes. So here methyl group is hindering the approach from the in the B, and that is why you will get a facial selectivity, that is reversal from the reaction A. That is why all of the above the correct one. So is it clear, guys? Everyone understood this concept? Okay, if yes, then I'm moving forward. So in problem number 10, they are asking you, in the reaction shown below, identify the correct combination of intermediate P and the final product Q. So I have talked very much about this N-butyl lithium, LDA, in the previous lectures. So they are telling you to identify the B and the final product Q. So they have taken this hydrazine and they have treated it with excess butyl lithium. So now butyl lithium, what it will do? Butyl lithium being a base, what it will do? It will abstract a proton, right? So it can abstract a proton. Because the molecule is symmetrical, it can abstract a proton from here also. It can abstract a proton from here also, right? So if the abstraction is taking place, then what is happening? Your negative charge in conjugation with this double bond, it will go like this. So there is a negative charge that is forming on the nitrogen. So what is happening here? It is a named reaction known as Shapiro reaction. So in presence of butyl lithium, first of all, proton will abstract. It will go like this. Here you will get the negative charge form, right? So in this also you will get this negative charge, and here after the formation of this you will get the removal of this nitrogen, that is the nitrogen molecule, N2 molecule. How it is going to be happen? See, excess of butyl lithium will also abstract the proton from this NH, right? So it has multiple acidic protons to be abstracted. So if it is abstracting the proton from this side and forming a negative charge, it can also abstract a proton from the nitrogen, form a negative charge. So it can delocalize here, it can go here, and this nitrogen negative charge can be done. So here tosyl will leave out. I have told you tosyl being a good leaving group, so it will leave out to give you what? This imide complex. So basically this imide form, and this negative charge again goes here, and this particular bond goes here to give you the removal of N2 molecule. Similarly, in this case also, you will end up having a N2 removal, and what you are ending up at, this is the negative charge. This is the double bond which is forming after the delocalization of negative charge, and here also you are getting a negative charge after the removal of nitrogen. As here, at a double bond head, you are getting the negative charge form. As you have a butyl lithium in the reaction mixture, so there is a lithium trapping which is happening at the negative charge, because we know that lithium is positively charged, it is electropositive metal, so that is why it will trap this negative charge to give you this complex, lithiated complex. So here also you are getting this lithiated one. So now tell me which will be the correct option for P product.
For P, second option.
For P, the second option. Fine. So basically, for P, second and fourth are similar. So yes, you are getting this. How you are getting this? After the removal of N2 through the Shapiro reaction, there is a negative charge which is forming at this position and which is trapped by lithium. So that is why you are getting this lithium at this position. Fine. Now this is sorted. It is getting formed. Right. Now what is the next step? They have added aldehyde. They have added benzaldehyde in the reaction. So now what will happen? I have told you that if a carbon is attached to a metal, then it will become a nucleophilic carbon. Similarly, as we have discussed about this R magnesium bromide, that is what? A Grignard reagent, right? So basically RMgx, this is the classic example that this is the negative point, this is the positive point. So this is the nucleophile, this is the electrophile. So here also we have discussed about this R zinc, right? ZNX. So similarly, here also you are having this nucleophilic carbon and electropositive metal. So similarly, here you have the electropositive metal, electronegative, I mean nucleophilic carbon. So here there is a nucleophilic carbon which is present. So if you are attacking onto an aldehyde, then what will happen? Negative charge will attack onto your carbonyl carbon, right? Leaving you to formation of alcohol. So now, if it is the case, then what will happen? Which alcohol is going to be formed? So which will be the correct option for this Q?
Second option.
Second option, because here at this position you will get the formation of alcohol. Benzaldehyde PHCHO, which means this negative charge will attack on this carbonyl carbon, will go up, and you will get a OHPH at this position. So here you will get the P as this product, Q as this alcohol. So second option will be the correct one. So is it clear to everyone? This problem, anyone has any doubt regarding this? So if not, I am moving forward. So in problem number 11, I have not given you any of the options. So here I am just trying to express a rearrangement that is very much famous and also a very important rearrangement. So here in problem number 11, they are asking you write the major product of the following reaction. So you have to answer the product. So what is happening in this? So there is a alpha chloro cyclohexanone that is present. So they have treated it with base. So till now we are dealing with acids. So now we are dealing with base. So now what will the base do? It will abstract the acidic proton, right? So if you have this proton, that is the alpha proton, so now which proton is going to be abstracted by the base? HA or HB? So here what is happening? So first of all, your base will abstract this proton, that is HB. Why? Because after the generation of carbanion here, this anion can eliminate your leaving group, that is chlorine. Also, after generation of carbanion at this position, we know that chlorine is electronegative atom. It can handle a negative charge, but you can also see that it is having a lone pair of electrons, right? So it is also behaving as a releasing group. So that is why the negative charge is not going to be stabilized at the alpha position, which is adjacent to chlorine. So here B protons is getting eliminated. So after the formation of this negative charge, it is going to form the CC bond with this, and chlorine will leave out. What is happening here? See, CC bond is getting formed, this bond, and this bond is already there, right? So this is how it is looking like. This is a cyclopropane ring formation, and after that, as you have a base that is also nucleophilic in nature, so NaOH, sodium hydroxide being a base, it can abstract the acidic proton, but it can also behave as a nucleophile. So being a nucleophile, it will attack onto your carbonyl carbon. It is going up. Then what happen? A tetrahedral intermediate is going to be generated. Now this oxyanion will come down, and there is a bond cleavage basically. So either this bond is getting cleaved, or either this bond is getting cleaved. HA bond, HB bond. Because it is a symmetrical molecule, basically there is no other stabilization which is happening here. It is a symmetrical molecule. That is why either bond can break and give you the same molecule. If AB is this bond is getting cleaved, you will end up having this moiety only. If this bond is going to be cleaved, you will end up having the same moiety. But if there is a chance, if let's say it has a methyl, let's say it has a methyl group, and it doesn't have a methyl group. So what is happening here in the reaction? There is a negative charge formation, right? So there is a negative charge formation which is happening at this position or this position. So the stability of carbanion which is getting formed in this reaction will govern the breaking of the CC bond. If the stabilization at this point is higher, then this CC bond will get break. If the stabilization at this carbon is higher, then this CC bond will going to be break. So if we have methyl at this position, then which carbon is going to be breaked? The carbanion which is generating at carbon number 1, let's say, is stabilized in carbon number 2 because of the electron releasing effect of the methyl group. So it will destabilize the carbanion. So that is why this bond, this HA bond, is going to be cleaved if the R is methyl. But in this molecule, which I have provided is symmetrical in nature, so that is why either bond can give you cleavage of either of the bond will give you the same molecule. So here the stabilization of carbanion matters. So carbon which is stabilizing the carbanion will get cleaved. So here after cleavage you will get a negative charge here, which is taken care by the water molecule which is forming at the first step, because your base has abstracted the proton to give you the water molecule. So here it will abstract the proton from there and you will get this molecule. So is it clear the reaction mechanism? Anyone has any doubt regarding this? Okay, if not,
It is clear.
okay. If not, then I'm moving forward. So here, this is basically a name reaction known as Favorsky rearrangement reaction. So this is the mechanism for Favorsky rearrangement reaction. So whenever you have a alpha halo carbonyl compound, that is the alpha halo ketone, in the reactant, and you are treating it with base like sodium hydroxide, that is a nucleophilic base, you have you can see the rearrangement that is known as Favorsky rearrangement. Okay. So now coming to problem number 12. So in this problem number 12, they are asking you predict the final product of the following rearrangement reaction. So again you have to identify the product. So here they have treated this acid with this HN3 acid. So this acid is treated with this acid. So what is happening? I have told you that whenever you have treated an acid with the carbonyl compound or acid, uh, what will happen? Protonation of the carbonyl group takes place, right? So here the protonation will takes place from this side, because here this oxygen is also present in the case of acid. So protonation takes place, water molecule will get removed, and there is a carbocation which is generated at this molecule, and this hydroxoic acid HN3 will then attack onto your carbonyl carbon, being a nucleophile. How it is behaving as a nucleophile? So this middle, so this basically this nucleophile, sorry, this nitrogen is behaving as a nucleophile. So it has a lone pair of electron which is present. So that is why it is going to donate, and you will get this pointing. And after the removal of N2 here, then there is a migration which is forming. So basically, there is a nitrine which is there is a isocyanide which is forming. How the isocyanide is forming? This R bond which is connected to the carbon is moving towards the nitrogen. And while moving towards the nitrogen, what is happening? This N2 is leaving out. So here you will end up having a isocyanide moiety, which is this moiety. This is the isocyanide moiety. So what is happening from the starting? We have an acid, we are treating it with hydroxoic acid. What will happen? Acid get protonated. Then the acyl cation will form. This acyl cation is then trapped by the hydroxoic acid. So one of the nitrogen being nucleophilic in nature, it will trap it, and the two nitrogen will leave out as a neutral molecule, that is N2 molecule. After that, there is a migration which is taking place at this carbon. Why? At this nitrogen. Why? To neutralize the charge. So here, after neutralizing this charge of H, what is happening? There is a attack of water which is taking place. So here, where is the water coming from? This. As you know that this carbon is electrophilic in nature, that is why the water will attack on this carbon to give you this intermediate. So basically OH is getting formed. So here also you will get the CO2 elimination and you will get the amine formation. Basically, starting from the acid, you are getting an amine with one carbon less. So here, this is the which is the name reaction? What is the name of this reaction? Can anyone tell me? This is also a name reaction.
Smith's reaction.
Siemens reactions, right? So here, you will form the isocyanide.
Smith's reaction.
Yeah, isocyanide as a intermediate, and you will form starting from the acid. You will get a amine formation which is one carbon less, right? So based on this particular mechanism, what is happening? I'm just revising it again. So first of all, the acid will get protonated, water molecule liberate, and you will get a acyl cation. Now this will act as a nucleophile. It will attack onto your particular carbonyl carbon. There is a 1,2 carbon CN migration which is taking place with the removal of N2 molecule. Then the water molecule will trap onto your carbonyl carbon, and the removal of CO2 molecule, which is a, and again the neutral molecule will takes place to give you the amine formation. So based on this mechanism, now tell me what will be the possible product for this transformation. So we are getting an amine formation with one carbon less. So any guesses what could be the possible answer?
A.
A, right. So here you will get a
First one.
aniline formation. How? Just remove the CO2 molecule
Anyway,
because one of the carbon is going out, and you have to insert the amine group. So based on this particular mechanism, you can write the mechanism for this as well. So you will get the answer as aniline. Okay. So is it clear? So if it is clear, then I am moving forward to problem number 13. So in problem number 30, so you have to find out the major rearrangement product of this following reaction. So again, this is a very simple kind of problem, sorry, similar kind of problem which we have solved previously also. So now tell me which of the alcohol is getting protonated in this condition.
both are similar.
Yeah,
Anyway,
both are similar. So that is why either of them can protonate and can leave out to give you the carbocation. Doesn't matter because it is a symmetrical molecule, right? So here the environment is similar. So that is why your protonation is happening at one of the carbon, one of the oxygen, and what will happen after getting the OH2 formation? Let's say at this carbon, it will leave out to give you the positive charge at this place. So I have told you that there is a migration of the CC bond which can be possible from 5 to 6. So here there is a formation of the bond which is happening between this and this carbon, and cleavage of this particular carbon. So if it is getting cleaved, this bond, there is a positive charge which is forming at this position, which is again neutralized by the OH molecule. And after the stabilization, You will get this ketone molecule. So either way you can do it. Either you can protonate this particular molecule and can leave out this. You will end up having the same compound. Okay. So this is how you are going to think about the formation of carbocation, which one we have to move, how the stability will come. So these are the aspects which you have to keep in the mind while solving these kind of rearrangement problems. This is again the Wagner-Merwin rearrangement. So here also you need to think. Sorry, this is a pinocolon rearrangement. So here also you will need to think the stability of the carbocation. So initially it was the diol, that is the pinocol, and you are getting at the ketone, which is the pinacolon. Okay. So is it clear, all of you? The mechanism of this reaction, it is very similar to the particular question which we have solved earlier. So now tell me the correct option. So option number
Fourth option D.
option number one, 4. So basically, you're ending up having this compound that is present in option number. So if it is clear, I'm moving forward again. So here in problem number 14, they are asking you predict the major product in the following rearrangement reaction. So again, you have to find the product. So they have treated the diketone in the presence of base. Now tell me what will this base do? Is there any acidic proton which it can abstract? Any acidic proton present in the system?
No.
No. Then what next it will do? It will behave as a nucleophile, right? So base has two options to do, either to abstract the proton, second, either to react as a nucleophile. Okay. So if it is acting as a nucleophile, then tell me on which carbonyl carbon it will act. Carbonyl carbon 1 or carbonyl carbon
1.
2? 1. Right. Why 1? Because if you see at the carbon 2, there is the aniline basically moiety which is present. So here there is a delocalization which is present because NH2 is a electron releasing group. So because of the electron releasing nature, it is making this carbonyl carbon less electrophilic in nature, right? So electrophilicity is getting reduced than the carbon number 1. So here there is phenyl, nothing attached with it. That is why here the electrophilicity is neutral. But because of the presence of the para amino group, what is happening here? Due to the resonance, it is getting highly conjugated, and that is why here your carbonyl carbon electrophilicity is going down. So base will attack on that carbonyl carbon which is more electrophilic in nature, right? So here also you will get the attack at C1 because of the higher electrophilicity. Okay, sorted. You have done the attack of OH at this position. What will happen next? This is getting the OH, fine. A tetrahedral intermediate is forming, fine. What next? Can anyone tell me what next it will do? So make,
Migration of phenyl group.
sorry, migration, yeah. So to make it easy, what is happening here? First of all, you have this particular ring. The OH minus will attack onto this carbon, giving you this. So now, if your oxygen ion has to come down, right, there should be a migration of the ring. So either this phenyl group has to migrate or OH has to migrate. So I have told you many a time that if the migration has to happen, that group will migrate After the removal of that group, the positive charge is to be stabilized. So that group will stabilize the carbocation. So here phenyl group having the higher tendency to migrate than hydroxyl, it will migrate to the carbonyl group, and after the migration you will get this tetrahedral intermediate. Fine. So this tetrahedral intermediate is now trapping the proton, and you will get this alpha hydroxy acid formation. So here, what is happening first? There is a nucleophilic attack of the base. Then there is a migration which is depend on the migratory aptitude. So phenyl has a higher migratory aptitude than the hydroxyl group. So phenyl will migrate to the adjacent carbonyl group, and now the oxyanion which is forming will be trapping by the proton, and there is a proton transfer which is takes place to get you the alpha hydroxy acid as the product. Right? So is it clear the mechanism? Any doubts, any queries in this? Okay, if not, then tell me the correct answer.
First option.
First option, option number one. Right, you are getting a alpha hydroxy acid. Okay, so if it is clear, then I am moving forward to problem number 15. So in problem number 15, there again you need to identify the product. So they have treated this particular compound with H2O2 acetic acid. So what will happen? H2O2 with H2O2 and acetic acid, what will happen? What do you think? This is again, I have told you previously that MCPBA and H2O2 is giving similar kind of chemistry, that is the epoxidation and the bear vinegar. But I have told you that in that case, MCPBA, there is no competing reaction. That means there is no double bond which is present in the system previously. That is why that at that point, beer vinegar was the only reaction that is operative. But if you have a competition between this particular carbonyl compound and this double bond, then you have to think about it. Either this happening or this happening. So this is the challenge of this question. So what do you think will happen here?
Bear vinegar oxidation.
Bare vinegar oxidation. So why do you think bare vinegar oxidation, not epoxidation? So here you need to think that, okay. So here what is this? There is a bare vinegar oxidation which is happening. Why bare vinegar oxidation? Because the the double bond which is present here is not at all electron rich, right? So it is present as a electron deficient species. So that is why this H2O2 is not going to attack on that particular double bond. It is not in the electronics. It is not in the favor of the electronics to attack the to go for the epoxidation rather than the bare vinegar oxidation. So here, the four-membered ring having the high strain, it will prefer to go to the five-membered ring by going through the bare vinegar oxidation rather than to stay at four-membered and do an epoxidation at this site, right? So basically, the driving force for this particular transformation, that is the bare vinegar oxidation, is that your four-membered ring, which is highly strained, right? Whenever it faces a chance, or whenever it comes to it that it can release the strain, it prefer to release the strain first. Other thing next, okay. So here also you have the four-membered ring. So that is why this H2O2 first react onto your particular carbonyl carbon to give you this moiety and this oxyanion formation. And as I have told you that one of the bond has to migrate. So either bond A will migrate or bond B will migrate. If it is bond A, it is bond B. So it has to migrate, right? To add this oxygen. And then this OH will leave out. So, what do you think? Why HA is migrating? Why HB is migrating? If you migrate Hb, this particular bond, what is this? This is a secondary carbon, na? But here this is present at the tertiary carbon. So this center is high in electron density. That is why it is going to be migrate than the Hb center. So I have told you, higher the electron density, higher will be the chances of the migration. So here this HA's bond is going to be migrate rather than HB. So if it migrates, then what is happening? This bond is getting cleaved and this bond is getting formed. So there is a carbocation formation at this carbon, which again is trapped by the hydroxyl group to give you the ketone. So this is how you are having a alpha oxygen rather than the epoxidation. So here, because of the presence of highly strained four-membered ring, uh, it tends to release the ring strain. That is why here you are getting this particular air vinegar oxidation, not the epoxidation. So is this much clear to all of you? Okay, then if it is clear,
Yes,
then which is the correct option here? Option number C. Right? This is the correct option. So coming to the last problem of this session, that is problem number 16. So here you have to identify the major rearrangement product formed in the Coulombic reaction. So again you have to identify the product. So what is happening in the product in the reaction? This particular species is going to react with aluminum chloride, that is a Lewis acid, at 90 degrees centigrade. So what will happen? Can anyone tell me? What do you think? So basically, aluminum chloride being a Lewis acid will chelate with your oxygen. So acid everywhere you see it will chelate with your carbonyl oxygen. So how it is going to be happen? This is how it is going to be happen. So here the lone pair of oxygen will chelate with this particular aluminium, and what will happen? It makes this particular group as a good living group. So here your acyl cation is going to be leave out. So after making it electrophilic, this carbon, it is breaking the bond and going to form the acyl cation. So in the process of formation of acyl cation, now the Friedel-Crafts alkylation is going to happen. So now it is similar to phenol. So what is happening here? As you have the lone pair of oxygen which is present, it is electron releasing in nature, right? Similarly, like phenol, it is electron releasing. So I have told you that whenever you have electron releasing group and you are going to give the Friedel-Crafts alkylation, there could be two product which is possible, ortho and para product for electron releasing, right? So here also you can get ortho and para product. So para product is the dominant product, right? So if para product you are getting at RT, but what they are saying is when you heat up the reaction, you will get the ortho product, so which is more stable thermodynamically. Why? Can you tell me why ortho product is more stable than para product here in this case? Why it is the thermodynamic product, not the kinetic product, the ortho product?
intramolecular hydrogen bond.
Yeah, intramolecular hydrogen bonding. So here there is a intramolecular hydrogen bonding which is present, right? So that is why it is the thermodynamic control product rather than the kinetic control product. So because of the stability of this product, it is forming at high temperature. But at RT, when you done this reaction, you will get this particular para product. So now coming back to the question, now they are asking you at 90 degrees. So what do you think will be predominant, ortho or para product?
Ortho product.
Ortho product. So you will get an ortho product, that is this particular option, as the major product. So is it clear, all of you? The mechanism of this reaction, everything? Okay, then if it is clear, then I am stopping it for today. This is it for today. This is the last lecture. This is the last session for the course. So I'm done, and I'm just leaving the. Okay. Okay. So I hope all of you have understood what I have taught till
Thank
now.
you, ma'am, for excellent demonstration.
So thank you so much for joining the session. So I'm leaving for today, and I hope all of
Thank you,
these
ma'am.
8 lectures are helpful to you. And thank you so much for joining. So thank you. I'm leaving it.
Thank you, ma'am.
Thank you.